Let's now look into, good morning everyone. Let's look into the bearing problem. Now if we look at the tutorial 2, which we are looking at now, is we have this beam here, right? So it is 410 UB, 53.7 kg per meter, grade 1 steel 300 plus. It carries an ultimate point load. Basically that means it is your P star, point load of P80 kilonewton, and is laterally and torsionally restrained. See the language. Is laterally and torsionally restrained at A, B, and C. Can you see that? It clearly says that, okay. Check the bearing under point load at mid-span, assuming that the load is applied by means of a 310 UB cross beam. That's what I was talking about before. This beam, if you look at physically, this beam is like this. Say this is the beam. Say this is your flange. Flange, this is another flange, top flange, bottom flange of that beam, this beam, right? So this beam. And then the I beam, there's another I beam is sitting on that. And that is transferring the load to this beam at that particular point. See? So the beam flange is actually sitting on the beam itself. It is connected, maybe bolted or whatever. There are mechanism to transfer the connection and the loads. We'll come into that connection, what kind of connections we need to have, but not at this point of time. We are not looking at connection here. We are talking about, imagine if this beam is transferring the load at this point. That's what we have talked about. It is really restraining the beam at this point, both laterally and torsionally, okay? Then you check whether this beam is going to fail or it's safe, the bearing under the point load at mid-span. Now, what do you mean by bearing in this case? This is a compression. You see, imagine what is happening at that point. A concentrated load is applied. Now, that concentrated load in that case can cause a localized failure or bearing failure. That's what we want to check the bearing here. Okay, so we are going to want to check bearing. Now, let's go back to the solution. So what you have to do is, you have to use this one, R star. R star means which is the bearing force. Now, if you say, what is this? R stands for? R stands for the reaction. That's why it is R. So it is a reaction which is R star. Star actually means the factor bearing force or the reaction. And the design principle is given by this. R star less than equals 5 times RB. What is RB? RB is the bearing capacity. So it is your section. So it's the section 5.13. This is a very important section for bearing. Section 5.13. We are looking at bearing. So section 5.13 is a compressive bearing action on the edge of the web. Okay. Now, for that, we have to calculate the bearing capacity. So that is your R star, which is the design bearing force, and that must be less than equals to the bearing capacity, which is given by RB, and phi is 0.9, which is the capacity reduction factor. Now, before going further, it is important to think about that how the load will be dispersed from the top beam to the bottom beam. That is where it lies the problem. How the load will be actually transferred. Now, we'll come into that in a minute. Before that, look at this statement. RB is lesser of RBY. That means it is called yield in bearing or the bearing yield capacity. And then the second one is called bearing buckling capacity. So if you read the section, it clearly talks about that. 5.1 to 13.3 and then 5.13.4 is bearing buckling capacity. That means in this case, what can happen is that two things can happen or two failure modes are possible. RBY, which is related to that bearing yield capacity, and RBB, which is the bearing buckling capacity. So lesser of the two will govern what is the bearing capacity of that at that point or the section, I would say, so that the section is safe. Now, first we have to calculate the bearing yield capacity. We are looking into that, how to calculate RBY. Now, for that, what I was talking about, the dispersion. Now, for the dispersion of load, now I will ask you this question. If you put something on the soil, say the foundation, how the load will be carried by the soil? How the load will be transferred to soil when something is sitting on the soil? Where you have showed uniform and all, these are very approximation. Too much approximation is involved there. Well, we have factor of safety, we know things work, so we are following that. But the question is, if you look at actual load transfer, how the soil will be how the soil will carry the load?
Well, the load starts at basically at the width of the applied load, then disperses as you go deeper into the soil.
Very good. So that means it will be dispersed through the soil. Very good. That's why we have the pressure bulb, Business equation and all, and the pressure bulbs and all. Very good. So it will be dispersed, that language. So here also what will happen is, here looking at a different dispersion problem. Different dispersion means, here the dispersion is through the wave and flange and those things. Here there is no soil here. But the mechanism will be again the same. Yes, it is dispersing. Very good, Robert. So the dispersion of that applied load, and how is it going to be dispersed? And now for that, look at figure 5.13, all those, figure 5.13.1.1, all these figure you need to do. Check. So I will draw one figure for you that is from 5.13.1.1. So if you look at the flange, this is your flange. Maybe use another color. So you have the flange. Okay. And then you have this RR, which is basically your the low, this flange. Okay. And this is your say BS. Now, what is the BS? BS actually is called, look at this language, it actually clearly tell you what is your BS. So BS is called the stiff bearing length. Now, that stiff bearing length is actually coming from, where? If you look at the top beam is like this. So this drawing of I section, ignore that, use scale and draw something. So if you look at the top beam, this one, which is from which this BS is coming. Okay, so this is your BS. So this BS is actually coming, if there's a load applied on the flange, then this load will be dispersed, So what I'm trying to say, when the load is applied through the wave, it will be dispersed through the flange, and this BS is basically the stiff bearing length through which the load will be transferred to the bottom beam. This is the bottom beam. This is the bottom beam. This is the bottom beam, and this is your top beam. Okay. So if you know BS, okay. So BS, if you look at the expression, it is the expression given here. You see this one. So BF means, suppose it is the flange thickness is given as TF, and the wave thickness is given by TW, then you are using this expression to calculate BS. So twice TF means, because you can see this is called 1:1 dispersion, 1:1. So 1:2 dispersion means if you have TF depth means TF on the horizontally also, 1:1 dispersion. So the important point is you have to think, what is the angle of the dispersion? That means, is it 1:1? Is it 1:5? That is important. What is 45 degree, 30? What is the dispersion? In this case, 1:1 dispersion, we have assumed, so twice TF plus TW plus this one. Now, this is the empirical one. This is due to the chamfer, this radius, this is bending radius is involved. So that just follow, that's just a approximation or empirical, I would say. So we have got BS, which is 39.9 meter. That means through that 39.9 millimeter, the load is being transferred to the bottom beam. Can you see that? So you are doing step by step. First, you are looking at what is happening to the top beam, because through which the load is being transferred. So you have calculated the stiff bearing length BS, and then that's the load through, that's the width through which the load is transferred to the bottom beam. Now, then we'll look at the other dispersion. See, this is one dispersion, which is the different color. So how many dispersions will be there? At the first stage, first it will be dispersed through the wave, right? So what is this one? So this is called 1:2.5. Again, if you ask me where is it coming from, again, this is from experimental, 1:2.5, very stiff. So that's the dispersion here. And then we have another dispersion. Usually we take up to the neutral axis and all, we don't go beyond that. So in this case, so if you think of this one, that means next case it is 1:1. So 1:1 means 45-degree dispersion. See? So that means the load is actually being dispersed through the wave. First, it is dispersed to the flange at 1:2.5. That's the, the dispersion, I'll say, angle. And then you have 1:1 through which, or the ratio through which it is transmitted or dispersed through the wave. So once we have done that, that actually means we have this width we have to calculate, right? Which we called BBF. That means at the junction, what is the width at the junction of the flange and the wave? That is called BBF. And then when it is transferred, to the wave up to the neutral axis, we consider. So that's your BBW, and this is your BBW. That means the extra dispersion because of the wave, BBW. Okay. So if you look at the total BB, this is your total bearing at the neutral axis. Can you see that? So we are talking about dispersion of load from the top beam to the bottom beam. First, we have explored how it is transferred or transmitted or dispersed through the top beam from wave to the flange. And then we got BS, the stiff bearing length. And then from that, it is dispersed to the flange of the bottom beam. First 1:2.5, then next 1:1 to the up to the neutral axis. So what is our job? Our job is to check what is your BBF. BBF is also a critical one. Why BBF is the critical one? Okay, because in this case, BBF, see, if you go to BB, we have actually a much longer length. So that's why BBF is critical. So we'll check BS, and then you have also checked BBF. So BBF in this case is 39.5 plus 5 times 10.9. This is 10.9. You can see why it is 5, because on both sides. So this much and this much. Okay. So both sides, 2.5 times 2. That's why it is 5. 5 times 1.9. So that's your BBF. So you have calculated BBF. And then TW, the wave thickness is 7.6 meter. So you can calculate RBY, the bearing yield capacity, as this one. Now, that junction is actually very, very critical, where it can actually yield, because a lot of load is being transferred to that junction point. So we are checking that what is the bearing yield capacity at that point. So if we look at the standard, it clearly says that you have to calculate the nominal bearing yield capacity at the of the wave will be calculated at the junction. Why is it at the junction? Because at that point, the length is minimum. You can see, look at the expression. The expression is this. The expression is given by this. So BBF, that's the lowest width, times TW, which is thickness of the wave, times Fy. And what is 1.25? That is some sort of factor. Okay, so if you plug in all those values, you calculate this one, RBY. Any question?
So BS doesn't actually reference the actual width of the web, of the flange of the beam acting on by the top beam.
Yes, exactly, yes, no. It may be equal, but many cases it may not be equal. No. Yes, correct. That is correct. So that means you can see, though it is physically sitting, but we have a width we are considering through which the load is being transferred, and this could be lower than, see, the tricky bit is this can be lower than the flange width. Yeah.
Okay. Yep. No worries.
Yeah. So bearing yield capacity from this expression, we have calculated 1.25 times BBF times TW times Fy. So you can see TW is the web thickness and BBF is the width. That means we are actually considering that if we have a plate, that one, TW, that's a web, you know, what is the width of that? That is thickness is TW, BBF is the length. That means that is the basically the cross-sectional area, or you can see the bearing area times the yield stress, Fy times 1.24. That's the bearing yield capacity. Now, next we look at the buckling capacity. Buckling, what it assumes is, again, look into the standard. What standard says is, we are considering that, yeah, so we are considering the buckling that the top and bottom flanges are effectively restrained against lateral movement out of the plane of the wave. Okay, no, sorry. So the nominal bearing buckling capacity for an I section or a C section wave without transverse stiffener, there is no stiffener. Because if you consider stiffener, then you have to add the capacity of the stiffener and then design them. Without the stiffener shall be taken as the axial compression capacity of the plate. That means wave you can think of a plate. So we are calculating what is the compression capacity of the wave plate, basically. Wave is considered as a plate. So you can see alpha B. What is alpha B? Remember that the material constant, you have done in compression. So alpha B, it is already given. So you don't have to do anything. Use alpha B equals 0.5. K form factor, it is given 1.0. Area of the wave is given by thickness of the wave times BB. Now in this case, you can see we are considering the whole, the length at the, or width at the neutral axis. So TW times BB. So we are calculating this, the area. That's the cross-sectional area, okay? That's TW times BB. LE over R, which is the slenderness ratio, isn't it? Because we are talking about buckling. So slenderness ratio, LE over R. This is an empirical expression already given in that section. So we are not doing anything. We are just following the standard in this case. This is an empirical expression of how to calculate the slenderness ratio of that plate. And then you calculate lambda n. As before, what we have done in compression, we already know that, section 6. All these expressions. So lambda n, slenderness ratio, and then alpha c from this table, alpha c 0.301. So now that means we are thinking of, if we have a plate, that's a wave, basically, it is subjected to a compressive force. What is the capacity of that under compression? So alpha c times ns, kf in Fy, this one. So in this case, you see RB is 287 kilonewton, and that actually, so RBY is 287, and then here you have got 348. So that actually means that the governing load or the governing bearing capacity is this one, because this is the lower of the two. That is 287, this is 348. That means yielding is critical here. So RB is 287, and then 5 times RB is 258, which is greater than the applied bearing force. So the bearing capacity is adequate here. Can you see that? Any question? This is an interesting problem, because how the load is actually transferred through the web, to the flange and the web, or even web and flange. It can be either way depending on the beam. So, and the load transfer direction. So then what you can see that how we can estimate the dispersion of the load to different elements, or I will say components. Is that clear, or any questions? So basically what we have done, okay, before going to the question, we have estimated bearing yield capacity, bearing buckling capacity, and you have considered which is the lower of the two, and then that is considered in the capacity of the section in bearing. Any question?
So is that bearing buckling capacity effectively ignoring the influence of the flanges? Just really looking at the
No.
strength of the web.
Absolutely, absolutely, yes. And in this case, what will happen is, if you look at in practice what we do, many times the web is going to fail in this, and then we will provide the transverse stiffener. That's the practice. That means you will have the web, we'll see, okay, this is failing in bearing or something. Then what we'll do is, there's a concentrated load means, major load means we will have stiffener. It's almost like a standard you could think of. So there will be stiffener added there. Transverse stiffness. So if you look at the next section, then that actually talks about all the stiffeners, how to design these different transverse web stiffeners. Okay. So basically stiffener, the word stiffener means, in this case, it is stiffening the web. That's the thing it is going to do. Stiffening that. That's why when you have the concentrated load applied, or even when the reaction, the support, we have these stiffeners to stiffen the web. Okay. How we can stiffen a flange? Web stiffener is fine. How I can stiffen a web, a flange if you need to?
Sorry, is that a genuine question there, Suresh, is it?
Yes.
Well,
Is
you
a
could,
genuine question.
yeah, you could do fillets along there if you wanted to, if you want to do it within the beam itself.
Good, yes. So you can have fillets. You can even add one plate on top of the flange, for example. Yeah, one could do that. Yeah, but the different things people could do. Yes, good. Fillet, yes. Very good.
I mean, I suppose in a extreme case, you could actually put two of them side by side and fix them together as well if you really wanted to
Correct.
boost the
Yes.
capacity.
Yeah. 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 So we can, yeah, I mean, we can actually have a, like, this kind of box girder if we actually have that, if we have to have. One could have this kind of box girder also. Like this, so the wave is becoming very good at this flange, and then we'll provide stiffener again, because already two waves, but still you can provide more stiffeners in between. Yes, good. So the idea is we can have different types of sections. It is not just one type of section. You can have, it depends on the depending on the requirement, we can have different types of sections. Any more question? So have a look at this one example, this section 5.13, which talks about the bearing, which is an important one to look into. And shear can be dealt in a similar way. So if you look at the shear capacity of the web, section 5.11, section 5.11 is your shear. So that what it does is it actually talks about the shear capacity of the web. That means, again, you will find it talks about the basic relationship, phi times VV, where VV is the capacity of the web. Now, this VV is the nominal capacity of the web, which is determined based on two things. One is called shear yield capacity, VW, which is given by 0.6 times Fy times Aw. You see, this is very straightforward. So it is web area times Fy times 0.6 is the factor. So that's your shear yield capacity. AW is the gross cross-sectional area of the web, and the other one is the shear buckling capacity, which is given by this VB, which is given by alpha V times VW. But you can see must be less than VW. That means buckling can reduce the capacity. You cannot exceed the yield capacity, but you can calculate this alpha V, which actually takes care of that. Alpha V is a factor basically you have to determine. So if you have unstiffened wave, you calculate alpha V. Sorry, that term alpha V or stiffened wave is different. So alpha V, if you calculate, suppose this is 0.2 is fine. That 0.3, that means the capacity of the wave will be reduced by this much, 80% reduction if alpha V is 0.2. That means this will then govern the design. That means this you have to substitute VB, which is the lower of these two, because that will basically determine the capacity of the wave. Got the point? That means you can have, this is called yielding capacity of the wave, yield, and then this is the buckling capacity. So this is, I'll write this one, shear capacity of the wave, on the wave. Now to look at the expression of alpha V here from the standard, if you look at unstiffened wave, what alpha V is given by this? This is a bit of involved expression, basically, not much. You have, I mean, you don't have to remember this, that's good. Square. So dP over PW times square root of Fy over 250. Okay. Now, what does that actually means? What are the parameters involved here? Fy over 250, that's the, we know yield stress. Now, dP over Pw. What is the Tw? Tw is the thickness of the web. So, what is the dP? dP is the depth, yeah? Depth, yes. dP is the depth. Now, for that, one important thing also you need to consider whether the shear stress distribution is uniform or non-uniform. If you have a approximately uniform shear distribution, then your VV will be equal to VW. Sorry, I mean, then the nominal shear capacity of the wave, where the stress distribution is approximately uniform, will be taken as this, VV equals VU. Okay. Now, then what we have to also do is you have to check this ratio, because depending on this ratio, we can actually have different situations. So if you have this dP over, okay, let's write it this one. If you have this ratio, add another page. Insert page. Move down. So what the standard says is, when you have the approximately uniform shear stress distribution, we will check the ratio of dP over Tw, depth over thickness. Okay. Now if it follows this one, 82 over, this is highly empirical, these relationships are. So Fy over 250, if this is, then we'll take Vu equals Vw. Okay. Now, if you see this other way around, that means this one is greater than this one, 82 over this one. Then we'll write Vu equals Vb. Can you see that? That means if your dP over T, that ratio is less than a certain value, then automatically nominal capacity of the shear capacity will be governed by this one, which is your yield capacity. That means this is yielding. This is yielding behavior. No buckling. And if slenderness ratio basically, this is too high, then it will be governed by buckling. Sure. Okay. So you can see that this boils down to check the ratio dp over tw, and then see which mode of failure is actually governs. And then you could write that is your VV. Okay. Any question? So basically, if you have to design the shear capacity, if you have approximately uniform shear distribution, first check these ratios, because that will govern what type of failure mode. And then you calculate the capacity, what we have shown here, BW and BV. And then from that, you look at this basic equation. So solve a problem. If you have an issue, you can check any section and solve, and then any issue, again, we can discuss later in the next class. Any question online before we stop today?
I was just going to ask, when's the next class? Have you guys got a break coming up?
Yes. So you have 2 weeks break. So the next class will be on 8th of July, Monday.
Thank you.
Thank you. Yeah. And I hope it was interesting. See, because we have talked a lot about the bending and bearing and then shear. So please have a look. I think it would be good if you can study something, because that will help you to do the assignment later. Yeah. Okay. Good. Thank you.
Thank you.
Thank you.